Welcome to this morning's talk by Dr. Angelos Voridas. Before his talk, I was just want to introduce him a little bit. Dr. Voridas, he is a native of Greece, and I don't know from which town he was born. Maybe he will tell us. And he did his undergraduate, in Greece, and afterward he migrated to United States, as many excellent Greek scientists do. And he did his graduate study in New Mexico Institute of Mining Technology. And there already he started working on the solar radio physics, right? Yeah. And he never gave up. He stay on in the field in solar physics, and he was also one time a assistant professor at the George Mason University, joining the physics group there, and eventually, he went to the Johns Hopkins University, the Applied Physics Lab, which you might have heard, many things about this famous scientific laboratory already. And Dr. Voridas, he is now I think you're the supervisor or leader of the solar heliophysics group, right?
Yes.
And
yes.
Which is a very prominent position. Even though he's very modest, his group is not well treated at APL.
Yes.
But he's doing very well. I mean, if you look at his Google Scholar, he has a large number of high index and tremendous. Okay, and without further ado, I will ask Dr. Angelos to start the talk. Angelos, please.
Yes, thank you, Dr. Ip, for inviting me, and good morning to everyone. I'll try to go slow because I know my accent is not really the best English accent around. So going with the theme of your seminar is to talk about CubeSats. Well, I was trying to think what I could bring to your attention. That is, and so I thought about a lot of recent work that we've been doing in the U.S. in the heliophysics basically community in preparation for our big 10-year plan, our decadal survey, as it's called, that determines the science and of course some of the space hardware that NASA will build from 2024 to 2025 to 2035. So what we've been working a lot was on the space weather aspects of the solar physics Sun-Earth system, and so I would like to discuss with you not just a single CubeSat or a small sat, but more of an architecture that seems to be emerging as a very popular concept for multiple missions in the Sun-Earth system. So my talk is organized, of course, I'll give you a brief overview of the space, why we're doing space weather research, and fill you in on what is going on in the US over the last few years, because there has been a lot of activity on this front, and we benefiting, people that work with the geospace or the sun have been benefiting on that. And then I wanted to discuss some ideas of how we can approach this problem of space weather, and give you some examples of small architectures, small sat architectures that can actually help, I think, is my opinion. So first of all, I know that Taiwan is pretty big on space weather, particularly atmospheric experiments. But that's just to get everybody on the same page. This is some sort of an overall graphic of why the space weather and particularly the sun matters. As you can see here, the sun with its explosive activity, both in terms of coronal mass ejections and with light, irradiance from solar flares and radio bursts, basically drives a whole set of phenomena in our near Earth space all the way down to the ground. And I believe you are familiar, of course, with the ground-induced currents that magnetic storms can create in the northern and extreme northern and extreme southern latitudes, and even the aviation, as now a lot of the flights go over the poles and therefore are susceptible to the radiation environment over the poles. So, because of this realization of the importance of space weather in everyday life, the U.S. government and other governments around the world have really started focusing efforts on understanding space weather and, of course, finding ways to mitigate the effects of space weather on the various systems. And that, of course, has, in a sense, benefited both the research and the operational communities. Now, there has been a very recent development in the United States. Late last year, a law has passed where the U.S. government made a commitment to address the space weather, the recognized space weather as a important aspect of national security and social impact, and they have created the law. It's the first time that space weather becomes a law. That law is called PROSFIT, and you probably will hear about it a lot in the coming months and years. Now, this law has directed NASA in this particular case, that's what I'll be talking about, to basically find ways to improve research. And so we were instructed by NASA to do an observational gap analysis. This has just come out. You can find it in the NASA website where the space weather is in the heliophysics division, which we did. You can see here with several colleagues from the United States, where we tried to look at where we're standing now in terms of space weather and what do we need. Where are the gaps? What observations do we need to do to become solving the problem? Trying to be able to forecast more accurately. When a CME will come, when a flare might happen, what the effects of those phenomena will be in the geospace. At the same time, again, as you very well know, there's been such a big growth in the field of small sats. The commercial sector has come in. The universities, even small universities, can now launch CubeSats. So there are a lot of new players in the field of space. So they have a lot of access to space. And so this has prompted NASA also to take another look at the way they run missions. So this is another task that we've been given to look, in this case, to look at the NASA program that deals with the Sun-Earth relations and try to figure out, where do we stand in terms of those programs. And this is the second line here to try to identify what should be the future heliophysics division program architecture. So that means missions. And for many of us, that means, of course, to examine whether new types of spacecraft, small sats, CubeSats, maybe nanosats, can play a role in this research arena. And so this work is still ongoing, but has led to us in the committee. I'm part of the committee to study different mission ideas and see if small sats can help, right? Instead of having to do these big missions that happen once every, 5-6 years. So how do we think we can approach the space weather problem? For any of you that have been, dealing with this, you know that the Sun-Earth system is complex. The phenomena can look chaotic at times, and but yet our communities, I'm more of a solar person. People over there in Taiwan may be more of a atmospheric or magnetospheric. We tend to look only within our communities and not talk too much across the interfaces. So obviously, I believe it's obvious. The way to go forward is to start talking to each other and meshing our knowledge and understanding of physics across this system. So therefore, approaching the problem as a system, the Sun-Earth problem. A way that we have, me and my colleagues, we're trying to come up with that, and I'm going to present this as an example that, and I would like to hear your opinion about it, is to come in from a physics perspective. You know, physics is all about the interfaces between, you know, liquid and solid, or liquid and air. And so the Sun-Earth system is similarly dictated by interfaces. So we have some key ones, which is, of course, when we go from the chromosphere, which is a high beta plasma, basically dominated mostly by plasma motions, to the corona, which has very beautiful images that are basically created by the plasma following the magnetic field lines, so very low beta. Now, as the solar activity goes out, there is another important interface when the wind becomes superalfenic, and that means, of course, that information cannot really propagate backwards so easily. You know, the structures have basically isolated themselves from their original driver or source region in the sun. And now they're propagating into the inner heliosphere, where they can interact with each other or with the background wind, until they come to our main interface, right? Between solar wind, and here I put all geospace into one, because it's a geospace by itself is a very complicated system. So if you think of those boundaries, then you can see how information and what information you want to flow across those boundaries. And here is an example. Usually we need to know the solar state, or equation of state. And the main thing that we want for a lot of the space weather analysis is really the magnetic field in the photosphere, since this is what defines the magnetic structure of the heliosphere and how Earth interacts with that structure. Then we have the corona, which is the seat of pretty much all the activities that we care about at Earth: flares, coronal mass ejections, jets, energetic particles, and of course irradiance changes, particularly in the short wavelengths, soft X-rays to extreme ultraviolet. Then, of course, the CMEs come out in the corona, and the ones that become superalfenic, well, then is this big, huge space between, say, the corona of the sun and the Earth, of several, hundreds, of a few hundred of solar radii, where the CMEs interact. They may change the shape, the magnetic field configuration, but yet these are the inputs that we know that they drive the response of the geospace. How fast is the CME, how magnetic, what is the magnetic profile of the part of the CME that intersects the magnetosphere, how long the interaction lasts. So at least if you set this, and of course I'm simplifying, right? I'm simplifying a lot the problem. But if you set it into this sort of 4 equations of state, now you can come and say, okay, what kind of equations do I need? And you can then create this, and I call them here observatories, but of course I mean multiple measurements. But and I'm not going to go into the details. I mean, we can discuss later. But this is sort of the way to break the problem into different pieces that we can sort of ingest, and make progress. So the problem I'm going to focus now, of course, is the really big problem. The gorilla in the room, as we say in America, and it is the scale. I mean, it's really the spatial scale of the system. Here I have a simulation from an MHD model of a CME propagating out in the inner heliosphere. And I try to put things in scale, but of course, you cannot see, even the sun cannot be seen in this scale. I had to blow it up by 10 times. And of course, Earth by 1,000 times to just make this little blob. And I put here in red the location of L1, which is sort of the most advanced location where we can make measurements of the incoming structures and use them to drive our models and to some extent do our predictions of what's coming to Earth. And now you can see that, okay, we have infrastructure around, at L1 that is operational nowadays, operational spacecraft that they do in situ measurements. So they basically take a trace in magnetic field, density, temperature, and velocity of the incoming, whatever is the solar wind. But that's only one trace. And as you can see here, I hope you can tell, the structure we're dealing with, it's immense. So one would say, and I've said that many times, so what's the point of measuring just 1 point? How can you predict things, even though L1 is just 1% from Earth, 1% of the total distance from the sun? Now, we do have other assets like the stereo mission, from which I've been involved from the beginning, and I'm the project scientist of the imagers, the imaging payload on stereo. And here is a composite picture of the CME, or of the heliosphere, as viewed from about the L4 point, 60 degrees ahead of Earth, of a transient coming towards Earth. So we can see the Earth. We can see a large front that may be a CME, maybe it's the shock driven by the CME. But you can see, of course, that this is barely detectable. You can kind of tell that our sensitivity is not so great, of course, because this structure here that you see as a front is about 12 to 13 orders of magnitude fainter than the sun. So it requires quite a lot of instrumentation, high sophisticated instrumentation and image acquisition techniques to get that image. And even though you get the image, still what you see though is an optically thin emission. So basically you see in the projection of a three-dimensional object onto your instantaneous sky plane. So that really makes it difficult to figure out, the 3D structure of a complex magnetic cloud as it is coming out of the simulation. So how we go about it? How can we solve this problem? Well, of course, we have to start from what we already know, and this is a composite of all the telescopes on stereo, from the stereo that is ahead on the right-hand side and the stereo spacecraft that is behind the Earth on the left-hand side. So if I put them together, basically I can create an almost 3D view of the ecliptic plane of basically and I can kind of see the structures that are coming towards Earth because they appear as halos. And by the way, of course, I can see the Earth on either instrument. So this is the best, this is the state of the art, if you like, that we had in the 2000s, at the end of 2000. This is a 2010 image. So how we can do better? Well, we know from analyzing these types of data that, of course, we don't have enough sensitivity to look at the small details inside the CME, and that we take a long time. It takes almost 80 minutes to make the image in blue. You have to accumulate for 80 minutes. So we don't, things are getting smeared. We don't really understand a lot of the interactions that happen so far away from the sun, in the middle inner heliosphere, if you like. So how we can do better? Well, that's really the driving from one mission study that I initiated as part of the LWS architecture, which is called SELOS, Sun Earthline Observing System. And you can see here that I'm not talking really about one mission, but I'm thinking of an architecture of hopefully multiple missions that will have similar designs, but they will go off under different science objectives. So here I can't tell you the end result. What I was envisioning is to have two observatories comprised of multiple spacecraft, one going towards the L4, which is ahead of Earth, the L4 Lagrangian point, and the other one going towards the L5, but not staying there. That's the difference. A lot of the operational observing program ideas that circulate, they have the observatory basically park at L5 so that you have like a permanent view of the Sun-Earth line. And so therefore image the CMEs presumably as they come to Earth. That may be okay for operations, but for doing research, which means coming up with the answers, this is not sufficient. There is a lot more information we can extract if we allow our spacecraft to basically orbit around this L4 point. And that's what this sort of banana-shaped clouds meant to represent. And I get you the details right away. So that's one thing, which allows us, for example, you can think of if I have an imager that looks on the surface of the sun, magnetic field, or extreme ultraviolet, but as I'm moving in my orbit, I basically cover a bigger part of the surface of the sun. And so when the observatories say are 90 degrees from Earth, I get 180 degree, almost 360 degrees, coverage of the magnetic field of the sun. Right? That's something we didn't have in stereo, and it is absolutely essential, we found, in all these different works with the committees and, of course, in the research that I've been doing, that is essential to have an accurate representation of the magnetic field on the surface of the sun, because that's the boundary that drives heliospheric models. So that's what gives you a more reliable modeling of the 3D heliosphere. And so if you have a more reliable modeling of what is the background wind, then when you eject the CME in your model, obviously you expect to get a more accurate result. You know, you expect to see the interplay between the CME and the background sources to be more realistic. But you know, that's what it matters here. These are not big spacecraft. What I had instructed the Goddard Space Flight Center Mission Design Laboratory is that I want to have this mission with rideshare spacecraft like ESPA class, so that they can be hosted, they can be added onto a ring, right, during the launch of a primary mission to use of the extra mass that is available. Now, not only I want the spacecraft to be relatively small so they can be accommodated in this architecture, I want them to carry their own CubeSats, take them to L5 and release them there, as you can see here in this little insert, where I have representative distances, to release them there to do in situ measurements. That way, I can separate the in situ measurements that they usually need the spacecraft to spin so they can cover a bigger part of the phase space from the imagers that they want to be looking very accurately towards the sun. But of course, the CubeSats being, as you very well know, small, it's very difficult to communicate with Earth. So the concept that I had is that the mothership, if you like, the ESPA class bus, will act as the ground station for all its surrounding CubeSats, and therefore the communication between the ground is done only through the mothership, and the daughter ships only communicate with the mothership. That simplifies operations a lot, as you can imagine. And so they can send data across. They can the mothership maybe can direct the CubeSats to change their observing program. For example, if there is detection of an oncoming CME, say, towards the spacecraft at L5, maybe the program can change so they can do more high cadence measurements. So this was the idea, and once I started thinking about the program, the science objectives that we could address, I really came up with pretty much everything that we can address that deals with coronal mass ejections at least, and by extension with shocks, which I didn't put here, but it is the same thing: shock initiation, shock formation, shock propagation, and energetic particles. And of the modeling of the background heliosphere, this objective 4, I put it in the end, but it's really the sort of the driving science objective. Try to get as much of the photospheric magnetic field instantaneously as possible, so that we can drive the models of the inner heliosphere. And so we can discuss this, of course, later. The instruments that I thought about, of course, I just took the instruments that we've flown before. So I wanted to have something that is has high heritage and to be conservative, because I know, of course, that the sizes get smaller every year. So if I could design a set of spacecraft that can accommodate older instruments, that means they can accommodate more of the newer instruments, so they can be more flexible. And that's really what I'm after. I'm after something that can be reused, in architecture, not just a mission. So here is typical difficult sizes, except for this vector magnetograph, which is not yet flown, but it is TRL-6, so it is undergoing space qualification right now. Everything else is flown, and it's pretty solid numbers. So the good thing, of course, is that even though I gave them those numbers, they came back and they said, okay, sure, we can do this. Here are typical the requirements I gave to the systems engineers. We want to have just daily downlinks. Of course, I'm not thinking of space weather operationally, right? I'm thinking of space weather research. So we don't need to have low latency. And I wanted to basically see what technology we need to develop to make such a system realistic. So, and here is really a lot of this is the orbit dynamics. Here is a snapshot that shows that, yes, you can launch both of these spacecraft along with their CubeSats on a single launch, send them to L1, use the maneuvers around the L1 to send one to L4 and the other one to L5, and indeed get them into an orbit. And please pay attention where the L4 is, the L4 focus is of the orbit. As you can see, basically, the spacecraft spends a lot of time away from L4, basically looking over the limb of the sun that is not visible from Earth, instead of staying at 60 degrees. And this is key for, of course, better science, because you basically observe something that cannot be observed otherwise. Now, this initial study we did, we couldn't quite get the L5, but they told me, of course, if we have more time, we can get it. And so here is the movie. It's always good to look at the movie of how this mission could be accomplished. So it takes about a couple of years. You see, this is the first year, and I believe is the second year when you have the little turn, and then the insertion of the L4 spacecraft. So L4 gets in there first. We start doing observations over the west limb of the sun, and then the L5 comes later. But of course, we can always observe the sun during the whole mission. The only problem is we cannot have in situ measurements because the CubeSats are actually still in their launchers on top of its spacecraft. So I'll show you this sort of Stroman payload. This is a payload that is about 1 meter tall, so maybe a cubic meter, more or less, that accommodates an antenna. This is a Ka antenna of about 1 meter, I think. So I can send a lot of data back to Earth. So we can put all the remote sensing images here, and this is the site that is of interest to you. This is where we're going to have the launch, the CubeSats, and with their release systems. Now the CubeSats, I took something that has already flown. This is and the Goddard people had information about. This is a CubeSat launched from Goddard at GTO. So it is quite, I call it space, I call it space radiation tolerant. And this was an a 6U. I wanted to do an 8U so that we can have space for maybe more shielding, right? Because we're talking about deep space CubeSats. We want them to survive for a couple of years, at least in deep space. We're gonna have beefier, of course, electronics and all that. But I also want to have more options for in situ payload. At the moment, I'm only thinking of magnetometers and the plasma measurements. Maybe an occasional energetic particle measurement. But other people might want to put composition. They might want to add more capability to this. So I don't want to restrict the mission design. And of course, they will communicate with an existing radio from what I'm told at Goddard. They have a radio that communicates back and forth with the mothership over this distance, say 10,000 kilometers. We will use autonomy they will have propulsion too. So that we're going to use the propulsion along with an autonomy system that will prevent them from drifting too far away from the mothership, so that we maximize the communications, the data transmission onto the mothership. This is now a study that we are actually about to do at the Payload Design Laboratory at Goddard, where we're going to study the release system of the CubeSats. And of course, the modifications, this what I call here deep space mods, the modifications that we need to make onto the system to make it survive in deep space. We have already developed some of the initial interfaces. For example, we're going to keep the CubeSats during transit. You'll be able to check for aliveness, so they will be able to have an active port to send housekeeping data to the main ship while they're attached to it. Probably we want to keep them warm, so we're going to have the heaters running. But I believe that's about it. We will see after we finish the study if we need to do more. So the good thing, of course, is that, well, first of all, that this is doable. And this is doable. In principle, you could launch it in 5 years. That kind of timetable I'm talking about, right? So we can do it right away. The very interesting thing from my perspective, because I like new and shiny technology, is that we came up with at least 4 ideas for further technology development. Of course, one is this intersat communications. In the beginning, I only consider mothership to daughtership, but I believe we can do daughtership to daughtership communications, which then allows me to do what? Well, if I have a transceiver on either of these CubeSats, I could do an active radio probing of the environment between any 2 of those motherships, right? I can basically send an RF signal or a UHF or even X-band signal between them, coded. I was thinking of a square wave, be detected on the other on the receiving spacecraft, and then by comparing with basically what it was expected to receive, maybe figure out whether there's been a Faraday rotation, because there's a magnetic structure crossing it, or some density perturbation. So that way you can have not only in situ measurements, say in those 4 or 5 locations, but measurements of the plasma state across this, 10 baselines. this is really number one in my agenda. Of course, we have to see what we need to do to make the CubeSats deep space so they can survive, the deployment system, and what I just told you about the autonomy. An example is to keep them in a certain distance from the mothership. The other one is, of course, to enable crosstalk to probe the medium in between any pair. So this is really kind of my final slide. And this tells you the vision that is coming out from these studies that we've been doing so far of how the heliophysics observing system will look like maybe by 2050. And the important thing that you see, of course, this is the 4-pi concept of having been able to image the sun as we do the Earth, right? To image the whole sphere by having a spacecraft off the ecliptic. Those would be small spacecraft again. It may be in different planes, so we can get coverage most of the time. And having, as you can see here, multiple constellations, and each of these constellations, you basically can think of what I just described, a mothership with 4, 5, 6 to 8 U CubeSats around it, that they will be optimized to do a particular measurement. Maybe they'll be doing energetic particle measurements, and they will be at a certain distance. Maybe they want to do turbulence measurements, so they have to be in a closer distance, and they will have to carry plasma and magnetic field measurements, and so forth. And then, of course, being placed in different orbits, either these extended orbits in the L4 and L5, which can then be left to decay. And as the spacecraft decays away from this orbit, it will actually continue to orbit farther behind the sun. So if you have the system replenishing itself, that's why I call it a system, then you might end up in the future having a sequence of spacecraft along one AU that they can communicate with each other and then with Earth. That's, of course, this is the future vision for the younger generation, not to me. But also explore other orbits like what I have here as quasi-satellite orbits, which is basically elliptical orbits around Earth. And so from the perspective of Earth, you see the satellite going around you. And that is a way to basically place satellites ahead of the L1 point. And if you have enough of them, say you can always have a pair or a single spacecraft very close to the Sun-Earth line so they can see an incoming transient. And so I think this is my last slide. This is not all for heliosphere. Of course, I talked about heliosphere because that's where I know, but we have looked very intensely into the other system, the geospace system, and trying to come up with similar concepts. Of course, they're not deep space, but very similar concepts to provide coverage for both remote sensing and in situ. And of course, I'll be happy to talk to you about that in the future once we finish those studies. Those studies have not finished yet, so I can give you like a good example. So this is really what I have, and I hope you found it interesting. And I want to hear your questions and ideas. Thank you.
Yeah, thank you, Angelos. So there are some questions. I have a number of questions, but then I see that there's always a student, Lin Qihong. You want to ask the question. Lin Qihong, would you like to unmute yourself and ask your questions first?
Okay. So now I can ask the question now.
Yes.
Yes, please.
Okay. So good morning, teacher. So I have 2 questions for you. So the first one is we know the moons in the 1 month inside has something times their position is between the Earth and the Sun. So my question is if this time and have the 1 solar storm come from the Sun into the Earth, and because the moon is between the Earth and the Sun, and can the moon to lower this solar storm's the energy? This is the first question. So yeah.
No, because the moon and the Earth itself are too small compared to the solar structure that is coming in terms of total energy. They are basically inconsequential to the amount of energy that the sun is sending to Earth. You can think of it that at the time of impact, you have about 10 to the 15 grams of plasma going at the speed of say 600 kilometers per second. So these are many joules, 10 to the 30 so joules of energy coming through, and the Earth is just I don't know. It doesn't even show up in the map. So no, there's no such effect.
Okay. So my second question is because you have said so there's a project to observe the sun. There's a project. You can to take the many satellite in the L4 and the L5, and the one major satellites and the four tiny cube satellites. So my question is that because this project, these missions, they are major missions to observe the sun and to predictions the space weather. So make the people looking to prevention come from the solar storms, the something bad energy. So my question is that because this project is just to predictions the Earth. This is tiny parts, the space weather. So if really is that, and you take the satellite in L4 and L5, and compared to the Earth, the satellites to the sun is the one slash line. In the slash line, there's a longer. So they have the higher requirements for the camera. And also, like your PPT to say, the satellites from Earth to L4 and L5, they need a longer time. So my question is, if we just to take off the two satellites to the Venus orbit, so the first ones, they are shorter distance for the sun, so they can do lower the requirement for the camera, and also one additional volume to observe the Venus. So it's another better method because if you take off the satellite to the L4 and L5, they will be expensive and need more time.
Yeah, the L4 and L5 are chosen because they are stable potentials, so it's easier to basically orbit a satellite around those potentials and do all these fancy orbits that I talked about. So from the gravity and dynamics, it's easy. And the other thing, of course, is that with those satellites, they're always at the same point. They're always ahead of Earth or behind the Earth. So you kind of know what you observe from the sun. If you put them in Venus, of course, say if you place them around Venus, they will go around the sun with Venus. So a lot of times will be behind the sun, so we cannot use them. So you would need a system that covers the whole Venus orbit to be able to do space weather prediction. But it is an option. It's not any cheaper. But what I want to study next, and I'm not really an expert in dynamics, is to have a satellite that orbits between L1 from Earth and the L2. Say the L2 will be somewhere here from Venus, right? So the L2 will be a little behind. Is always behind Venus, and the L1 is ahead of Earth, and those are presumably, unstable potentials, but still there might be a solution of an orbit that kind of goes between L1 and L2. So that way you might be able to place spacecraft in more advantageous positions. But this has to be studied.
Okay, thank you.
Sure.
Any other questions from the audience? If you have, please raise your hand or let me know, or unmute yourself. In the meanwhile, I have a couple questions to Angelo. The first one is that you may have already explained it, that maybe you could reiterate it again, because this is an important point. What is the major advantage of a combination of a mothership plus a number of CubeSats in comparison to a single spacecraft?
Yes, there are several advantages. One has to do more with the building of the mission. You know, if you have in situ instruments on the same bus as the remote sensing, of course, the in situ instruments, they put magnetic cleanness requirements and EMI, EMC requirements on the spacecraft. They have to have a boom. You have to test the boom. So there is a complication during the build of the spacecraft with a lot of requirements that have to be satisfied. So that costs money. The other thing is, of course, that by having taking the in situ instruments outside, you can make them spin. So instead of having, say, multiple heads of say, a Faraday cap to observe different directions in the solar wind or in Zetic particle, you can have a spinner. So that saves you money, presumably, and complexity. You don't have to have 4 different sensors on a spacecraft. So to me, that's the first one is complexity. The second one is resiliency, because if an instrument basically breaks, it's kind of independent, and so it doesn't impair the mission as much as, you know, if it was part of the system on the spacecraft. I mean, you can design the spacecraft to avoid that, but again, it's complexity. And the other one is that you can really allow them to go different distances, so you can adapt your measuring strategy as you learn more about the system. You know, for example, you might learn that the dominant structure of the solar wind is, you know, 10,000 kilometers apart, right? So you can push your instruments a little bit farther away and increase maybe the power output of the antenna to account for the distance. And now you can study different type of structure. That's really the benefits for me.
Well, I mean, in your scenario, you have, I mean, look at this picture. You have L4, you have L5, L1, L2. You know, you're supposed that NASA said, "Hey, Angelos, you're too greedy," you know.
Yes, I am.
As always, and I only have money for you. You know, only one. You know, one cluster. So the question is, actually, it's on the Lagrangian point, L4, L5, only one point, one location. And which one would you go?
Yeah, at this point, I would go to L4, and that's because the L4 is the optimal point to monitoring the sources of energetic particles, because of the shape of the Parker spiral. Particles that are sort of on the west hemisphere of the sun, they will follow the magnetic lines and impact the Earth and the Moon. So if I had astronauts in the Moon or outside of the Earth's magnetosphere, then this is really what I care about. I wanted to protect them as much as possible. Now, it's also good for a little bit for Mars, because I mean, of course, when the Mars is on that side, when you're on the other side, you need the L5. The other thing is that the Europeans are interested in putting a mission to L5 that is operational. It will stay at L5, and so if we only had to pick one, and assuming that the Europeans will come up with the money and do it, then I will do L4.
So L4 is good for Mars, and L5 is good for Earth.
L5 is good for Earth, yes, and predicting, you know, seeing new active regions popping up on the east limb of the sun. But L4 is better for energetic particles. So if you have astronaut bases in the Moon or people traveling to Mars, I believe this is the place you want to be, L4.
Okay. Another question is that since you're the big boss, you know, can you think of a scenario in which APL provides the mothership, and then you advertise and asking other people, other country to join you to provide the CubeSat. I mean, what I'm saying that because then in that way the Taiwan may able to participate.
Mm-hmm. Exactly, and this is, thank you for this, because this is another reason that we want to have multi-systems. That we were really focusing in our different committees on the systems is because it allows the funding agencies to say, okay, I can only do L4, and then come to Taiwan and say, or Japan, and say, do you want to do the L5? Or they can say, like you exactly told me, oh, NASA will build the mothership, but then it will ask Taiwan and maybe other smaller players in space, UAE or whatever, to bring in, to provide their own CubeSat, so that they will look like what it should be always, a true international mission, because that will be more fun.
Right.
Yes. This is we actually pushing not only through these types of missions, but in our reports to NASA, we are actually pushing this argument that if we break the system into multiple pieces, then we can invite more international collaboration to help.
Yeah. Well, as you know, that in Taiwan we are interested in space weather research.
Yes.
But it's almost impossible to think of having a standalone mission. Like you described.
Mm-hmm.
On the other hand, if it's a international cooperation, and in which we play we contribute some element of the mission.
Yes.
And
and I think this is up in the NASA is very interested in that, and actually it is part of the law. This law that I mentioned in my introduction, the PROSFIT, actually directs NASA and NOAA to look for international partners in solving the space weather problems that they have, the gaps. So I think it is very positive. Yeah.
So it makes makes sense for us here to look into such a mission.
Yes.
Yeah. And then maybe we'll write to you soon. About this possibility. Yeah.
That would be nice. Yeah. And so that's why I gave you this example, and I'm telling you this example of mothership and CubeSats is kind of like something that keeps coming up in a lot of our discussions. Not only for deep space, but also in geospace. It's just that those studies have not finished. We have a study when we want to kind of like the next generation after GDC and dynamic to try to image the EUV geocorona, to look at the outflow of species out in the magnetotail, to kind of study the Earth as an exoplanet, right? I want to see how much stuff is flowing out. So that will require putting spacecraft in the L2. So there it would make sense to have a constellation so that you can spread them out or spread them in depending on maybe the activity that's coming out from the sun,
So Angelo, if you want to have a partner, you could always count us in, we will be very interested in joining such
absolutely.
Yeah.
Of course, I'll be happy.
And then the Lin Chiong, who just asked you 2 questions, and he wants to have more, So Lin Chiong, then you ask Dr. Paulides again, please.
Okay, so can you hear me?
Yes.
Okay, so I have another question about CubeSat. So in PPT, in your speech inside, you have says 1 major satellite and 4 small cube satellite. So my question is that because, like you said, there's a cube satellite, it's HU, but the cube satellite, they have something bad qualities. First one, they are tiny, they are very small, so they cannot build a very good white pulse shell to prevent something tiniest rock to destroy it. And also, there's a CubeSats. They are easier to broken because their inside something structure, they are very fragile, also very small. And another one is to transport 1 major satellite and 4 tiny satellite. into the once a stable the L4 and L5 to transport the 5 satellite in the same time into the one sense point inside. I think this is one big technology challenge. So, do we should be just for the test and to take off this 5 satellite into the L4 and L5? Because I think if just for the test, we can to take there's a many CubeSats in the L1. They are shorter for Earth and also it's easier to go. So this is my
Yeah.
question.
So one of the problems basically that there are no CubeSats in deep space. The only ones that have flown out was the Marco pair that went to Mars, and they sent data back to Mars and survived 6 months in deep space. That's the only example that I know of. And of course, they were not cheap, right? They cost $10 million each. So the CubeSats are not going to really save you much money, but they cannot. What I said before is that they give you the ability to have a disaggregated mission design architecture, so that if you lose one piece, you don't lose the whole mission. You can have that for you. Now, of course, my opinion is that we have become a little bit lazy with the CubeSats. We got used to sending them out to LEO, survive for like 6 months, and be happy about it. Well, time for a new challenge. Can we make the CubeSats as robust or close to it as we do the regular satellites? And yes, this will require making them stronger structures, using high-rated electronics, do shielding. Okay, but that's a challenge, right? That's for you, the young people, to come up with the smart ideas of building those. Now, the example I have here, the what's the name, Dellinger, that has 2 magnetometers, and you can see this is 6U. Well, it went to GTO, so it survived a pretty, tough radiation environment. Actually, once you leave Earth, the radiation environment gets better. But that's what I'm saying here. This deep space modes, this deep space modes is what we need to be focusing on for the people that are experts in CubeSats. How do we make them strong enough to get them in outer space? The getting them out is not difficult. That's the second question, right? We have 4 spacecraft on the main one. I thought the same, that would be complicated. It is not. They are not really taking that much mass. We can launch this middle class CubeSat, small sat can be up to 600 kilograms. So that's a really, you have mass to carry out.
So any special device is necessary for this kind of CubeSat because their working environment is different for the low Earth orbit.
Yeah, you need to make them stronger. You cannot use off-the-shelf system so easy, or that's what I'm saying. This is the challenge. Can you come up with a mixture of the self-systems that you can adapt, piecewise? You do a little bit of shielding around a critical component, or you beef up a particular structure but not another one, or you use 3D printing to make a more complicated shape that protects your vulnerable components. And now we have a mixture of not a very expensive super duper satellite that costs $10 million, but you can do it with 6 or 7 million. Something that is the best of both worlds. And the other thing you should take into account is that we're talking about multiple CubeSats. So you're not going to build one. You usually, I hope, we usually will build up like 5 at a time. So we can replicate, buy more components and replicate them, and therefore save money that way.
So how about to fix this CubeSat on major satellite after they are stay in a L5 or L4 inside releasing? Because CubeSat, they just can carry very little fuel. They cannot do change orbit too much.
Well, that's what these ones will. They have to stay for 2 years. So you just have to build them strong enough to last for 2 years. I don't think that's a problem. That's what I'm saying, that you have to come up with smart ideas of how exactly to build a system that it will survive 2 years in deep space. I'm telling you, it's easier in deep space than in the radiation belts to make them survive.
So compared for this kind of very hard challenge to take off this full satellite into their orbit, how about we just to measure this CubeSats in a major satellite?
But remember, they will be in their own pods, deployment systems on the spacecraft. Okay, the mothership, and so they will fly all the way to say L4, and then be released at L4. And so they only need propellant for that amount of time, for 2 years, moving around in L4 and L5. And they only need to communicate with the mothership, so they don't need big antennas. They don't need as much power as they will otherwise.
So now we understand why Angelos is not so popular at APL, because it's giving the engineers so much trouble, you know.
Exactly. You have to be challenged. They have to be challenged.
All the challenges you could get from Angelos. Okay, good.
Well, in the end, it's just money. That's what they tell me. It's just money. Oh, it will cost you more. Like, well, it's not my money.
So the time is almost up, you know. But then thank you so much, Angelos. It's very interesting, and I think for the audience here, I mean, I think that maybe the message that you might be getting a space weather mission with the help of Angelos, right? And we will work on it. We will work on it. Perhaps we could go through using platform, you know, like a COSPA.
Yes, that's right. We also do. That's exactly right.
Yeah, you know that. Dane Baker, right? Dane Baker is very successful in launching a cluster, CubeSat constellation study. Yeah. So I think
all these are related. That's what I'm going to tell you, that there's a lot of interest in the community for these things from many different directions. But the bottom line is that we need, you know, these CubeSats, that they have to survive in deep space. They have to have this autonomy. These are the challenges for the engineers. And they
welcome challenges.
And we will do it. We will do it. If we work together, we will do it.
Okay, very good. Angelos, thank you so much for this wonderful talk. Yeah, and hope to talk to you again. Yeah, thank you.
I hope to see you in person sometime.
Yes, definitely. Yeah.
Bye, everybody.
Bye-bye.